So, what I wanted to talk to you about is the fact that certain wavelengths of light can actually vaporize water without the need for heat. This is known as the photomolecular effect, and it was discovered by MIT researchers, and this could affect calculations of climate change and may lead to improved desalination and drying processes. The article is written by David L. Chandler in the MIT News. The article was published on April 23rd, 2024. It continues research from last year, which discovered how this worked with using certain hydrogels, but now they've also discovered that it can happen without the hydrogels directly on the surface of water. So researchers at MIT have discovered a new phenomenon that light can cause evaporation of water from its surface without the need for heat. Let me repeat that again. They can evaporate water without the need for heat. The device is designed to measure a photomolecular effect using laser beams, and probably the ideal kind would be the green light laser beams, which are produced by diode lasers, and they should be at an angle of 45 degrees. But the article will explain that more later on. The authors say that the study suggests that the photomolecular effect should happen widely in nature, from clouds to fogs, ocean to soil surfaces, as well as plant transpiration. This has a lot of applications, Gang Chen says. Uh, there's also Guangxing Lev, as well as James Zhang and Yaodong Tu, who participate in this work. We're exploring all of these different directions, Chen says, and of course, it also affects the basic science, like the effects of cloud on climate, because the clouds are the most uncertain aspect of climate models. So I mean, literally, let's think about that. We know that the heat that comes from the rays of the sun helps to evaporate water because the water becomes eventually hot enough that some of the molecules will then break loose and go into the air as in the form of water vapor. But here we have the effect that's occurring not just simply because of the heat. Chen says this phenomenon should be very general, and our experiment is really just the beginning. So, in other words, they're cautioning that this is something that they have discovered, which is pretty revolutionary. It's something that really we haven't known before. And if you ask most scientists at this time, they're going to tell you you're crazy that this isn't possible. In fact, I think I tried to ask AI about it. AI, using a more dated database, actually indicated that it violates the laws of thermodynamics. But unfortunately, as it would seem, these researchers have made this great discovery. Evaporation is all around us, and humans have been observing it and making use of it for as long as we have existed. And yet, as it turns out, we've been missing a major part of the picture all along. We've assumed that it is only the heat that is responsible for the vaporization. And so, in a series of painstakingly precise experiments, these team of researchers at MIT demonstrated that heat isn't alone in causing water to evaporate. Light striking the water's surface where air and water meet can break water molecules away and they can float them into the air, causing evaporation in the absence of any source of heat. The astonishing discovery can have a wide range of significant implications. It could help explain mysterious measurements over the years of how sunlight affects clouds and therefore affect calculations of the effects of climate change on cloud cover as well as precipitation. It could also lead to new ways of designing industrial processes such as the solar powered desalination or the drying of materials. When you think about these findings and the many different lines of evidence that have demonstrated this new reality, this phenomenon is incredible. And the details of how it works are well described in the article, which I will actually link in the comments below, so that you not in the comments, in the little description section actually. And so it's described in the journal PNAS in a paper by Carl Richmond Soderberg, professor of power engineering Gang Chen, postdocs Guanxing Liv, as well as Yaodong Tu, and the graduate student James Zhang. The authors say their studies suggest that the effect should happen widely in nature, everywhere from the clouds to the fogs to the surfaces of oceans, soils, and plants, and that it could also lead to new practical applications, including in energy and clean water production. Chen says, I think this has a lot of applications. We're exploring all of these different directions, and of course, it also affects the basic science, like the effects of clouds on climate, because the clouds are the most uncertain aspect of climate models that we know of. So let's talk more about this newfound phenomenon. The work builds upon research which was reported last year, which described this new photomolecular effect, but the research last year really was under very specialized conditions. The surfaces that were used were the specially prepared hydrogels that were soaked with water. In this new study, the researchers demonstrate that the hydrogel is not, in fact, necessary for the process. It occurs at any water surface which is exposed to light, whether it's a flat surface like a body of water or a curved surface like a droplet of cloud vapor. Because the effect was so unexpected, the team worked to prove its existence with many different lines of evidence as possible. In other words, when you have something that people are going to be skeptical about, they obviously want to try to have as many arguments to try to defeat any counter arguments that people will raise. So they report actually using 14 different kinds of tests and measurements that they carried out to establish that the water was indeed evaporating. That is, molecules of water were being knocked loose from the water's surface and wafted into the air into the form of water vapor due to the light alone and not by heat, which was long assumed to be the only mechanism involved, right? Up to this point, as people as they understood thermodynamics, had always assumed that the heat was the only mechanism involved in making water vapor. And now we know that the light itself, without the need for heat, can do it on its own. I'm not going to say it does it on this wide, huge level, but it is a specific piece of the puzzle that we never knew about before. So they used a test container and they began to see the water escaping. The air temperature measured above the surface cooled down and leveled off, showing that thermal energy was not the driving force behind the effect. Other key indicators that showed up included the way the evaporation effect varied depending on the angle of the light, the exact color of the light, and its polarization. And this is what I discussed earlier when I said it needs to be a green light, it needs to be at a 45-degree angle, and it does need to be polarized. You cannot use non-polarized lasers for this point. So none of the varying characteristics should happen because at these wavelengths, water hardly absorbs light at all. And yet the researchers observed them. The effect is strongest when the light hits the water surface at an angle of 45 degrees, which I've been mentioning throughout this description. It is also strongest with a certain type of polarization, which is called transverse magnetic polarization or TM polarization. So it definitely has to be polarized, and it peaks in green light, which oddly is the color for which water is the most transparent and thus interacts the least, which is kind of counterintuitive, but nonetheless, this is what they've discovered. Chen and his co-researchers have proposed a physical mechanism that can help explain the angle and the polarization dependence of the effect, showing that the photons of light can impart a net force on water molecules at the water surface that is sufficient to knock them loose from the body of water. But they cannot yet account for the color dependence, which they say will require further study. Right? It's not easy being green, right? Um, mean green. They have named this the photomolecular effect by analogy with the photoelectric effect that was discovered by Heinrich Hertz in 1887 and finally explained by Albert Einstein in 1905. That effect was one of the first demonstrations that light also has particle characteristics which had major implications in physics and led to a wide variety of applications, including LEDs. Just as the photoelectric effect liberates electrons from atoms in a material in response to being hit by a photon of light, the photomolecular effect shows that photons can liberate entire molecules from a liquid surface, as per what the researchers are saying now. Which, I mean, I don't know if you're excited, but I'm excited. The finding of evaporation caused by light instead of heat provides a new disruptive knowledge of light-water interactions, says Xiulin Ruan, professor of mechanical engineering at Purdue University, who was not involved in the study, but was available for comment. It could help us gain new understanding of how sunlight interacts with cloud, fog, oceans, and other natural water bodies to affect weather and climate. It has significant potential practical applications, such as high performance water desalination driven by solar energy. Keep in mind that we're always looking for desalination techniques because we need water for various applications, industrial as well as for people, right? Because we don't drink salt water, right? We would die if we kept drinking salt water because we would be inundated by so much salt that it would affect our bodily system. So we need desalinated water, right? And so to be able to do this using this type of effect actually could go a long way in helping us reduce the costs of desalination. This is a mystery of climate science, which can now go into a lot of implications because we can learn a lot more about clouds because there are things about clouds that we don't always know, and this could help explain a piece of the puzzle. The additional evaporation caused by this effect could account for the long-standing discrepancy, which has been a subject of dispute since such measurements are difficult to make. Those experiments are based on satellite data and flight data, Chen explains. They fly an airplane on top of and below the clouds, and there are also data based on the ocean temperature and radiation balance. And they all conclude that there is more absorption by clouds than the theory could calculate. That's because under the existing laws of thermodynamics, they're not accounting for this effect. This effect is a newly discovered effect. So, therefore, due to the complexity of clouds and the difficulties of making such measurements, researchers have been debating whether such discrepancies are real or not. And now we have evidence that this discrepancy might be real and where this additional effect is coming from. And so, what we've discovered here suggests that, hey, there's another mechanism for cloud absorption which was not accounted for in the previous models, and that this mechanism might help to explain the discrepancies. That doesn't mean it's going to explain all the discrepancies. There may be still much more work to do here. But Chen says he recently spoke about the phenomenon at the American Physical Society conference, and that one physicist there who studies clouds and climate said they had never thought about this possibility. This could affect calculations of the complex effects of clouds on climate. The team concluded experiments using LED shining on artificial cloud chamber that they observed a heating of the fog, which was not supposed to happen, since water does not absorb in the visible spectrum. Such heating can be explained based on the photomolecular effect more easily, he says. Liv says that one of the many lines of evidence would be that the flat region in the air side temperature distribution above hot water will be the easiest for people to reproduce. That temperature profile is a signature that demonstrates the effect clearly, he says. Zhang adds, it is quite hard to explain how this kind of flat temperature profile comes about without invoking some other mechanism beyond the accepted theories of thermal evaporation. It ties together what a whole lot of people are reporting in their solar desalination devices, which again show evaporation rates that cannot be explained by the thermal input. I hope you enjoyed this. Please continue to read the MIT article for more information. This was just a brief summary. I didn't want this to go on too long. And if you're new here, I welcome you aboard. This is a safe space. If you're returning, thank you for your continued support. It's you that makes this channel possible. I love you. I love you. I love you. Thank you and have a wonderful, wonderful day. Take care.